All right, here we go. So that's what I got my own undergrad degree in back in the day. I've forgotten a lot of stuff because this is a long time ago, but I tried to compile over spring break the main points of what I do still remember. So if any of you guys go into civil engineering, there might be quite a few guys out there. Here's what I remember from my classes. So here's different categories of classes you would take. Take math classes up to there's a post-calculus class called differential equations. That was the highest class I had to take. I thought that was pretty tough, but that I think would be probably mostly important if you're doing like aeronautical engineering. There were some applications of that. Okay, so science classes here. Physics 2 is more focused on like electricity type physics, which I'm about to do with you guys. We'll do some basic circuits here in the next week. Okay, and then here's a bunch of engineering specific classes that you'll see the rest of this presentation. Okay. One little detail here. One of these I listed AutoCAD. The class itself wasn't called AutoCAD because I think it's like a brand name. So like a program you can like design structures and stuff. And so statics, one of the classes you take. You might remember last semester when we were studying forces. You guys remember these conditions for equilibrium? So the sum of the forces in each direction would have to zero out, right? And then by December, we added this third condition, the sum of the torque would go to zero. Now this is for a two-dimensional structure, like if you're looking at a two-dimensional plane like this. Okay? Now if you go to 3 dimensions, the sum of the forces along each of X, Y, and Z axes has to zero out, and then the torque along each of those axes would also zero out. So now what AP does not quite go into with torque is the right-hand rule. I did sort of teach it to you guys just very briefly. AP does clockwise, counterclockwise. But if here, show you guys that. Sorry if you guys were watching a video at home. I'm going to do a quick demo with the door. So just imagine if I'm turning this door from above, you might say, okay, it looks a bird's eye point of view. Would this door be turning like counterclockwise and then as it's closing like clockwise? Okay. So if you curl your fingers in the direction of that door, you guys see how my thumb is like pointing upward? That's like along the z-axis. If the floor is like on an XY plane, my thumb's pointing along the z-axis. So you can treat like counterclockwise and clockwise motions along like a perpendicular axis. You can define it that way. So it's kind of and when you get into matrix math, actually works out really nice in terms of the math. But how about this the static stuff? So let's say you're building like a truss bridge, right? You would want to know like what are the stresses on each part of this bridge. And if these conditions are true, if the forces and torques have to sum to zero, you can do these calculations. So you might pick like this joint point here, right here. And then you might want to figure out, well, is each of these pieces in compression or tension? When you guys built those toothpick bridges, right? That was a good question. It's like, well, what parts are going into tension? What parts are going into compression? And would the tension or compression exceed the maximum possible tension or compression of each part? You know, is this bar here like too skinny, or is it made out of the wrong material and it's just gonna like crack apart? Right? I should have expressed this as a trivia question, but like, what's the strongest arch shape that you can create? Let's say you have some confined space. You want to build like the strongest arch to carry the greatest load. So maybe some options could have been like a semicircle or like a parabola, but the answer is this: it's actually a catenary. Now, catenary has pretty crazy looking math, but physically it's actually very simple to create because it's the exact same shape you get from just hanging a chain, right? From 2 points. It creates a natural catenary. It looks like a parabola, but it's not quite a parabola. Now, if you take this and make it stiff and flip it upside down, you get a catenary arch. The St. Louis arch is a modified catenary arch. So fun trivia right there. I-beams, you see these all over the place. Now, why use an I-beam? Why does this have so much strength and has economical properties too? Right, so let's say you had this I-beam as part of your structure. Right? Now think about how your toothpick bridges would work right here. Actually, I'll flash this on the camera. You guys are watching it at home. You can see a little thumbnail version of this. Right? So you guys remember your bridges were on supported by 2 supports on the ends, and I put the load in the middle, so it wants to like bend like this, right? Remember that? And most of the tension stress was in the bottom of the bridge. Most of the compression stress was in the top. Right? You guys remember that? Well, imagine the same thing for that beam right there. If most of the tension is in the bottom, most of the compression is in the top. You guys see those flanges would have most of the material to be able to handle most of that stress. And then the stress would like zero out right in the middle. Okay, well, there's not very much material right in the middle, but there doesn't need to be because the stress approaches zero, like right in the middle, as there's that trade-off between tension and compression. Okay? Now, steel is a lot more expensive than concrete. So this is also an economical solution, right? If this is, for example, embedded in concrete, then right, so less costly. Now, that shape also gives it a moment of inertia, which is involved in strength of material. You guys ever looked at the side of a washing machine or a dryer? You see that like those indents, right? Those are intentionally manufactured there to give it some strength. Right? Like if it was just a flat sheet of metal, it might be a lot easier to collapse if you put it like too big a weight. But if you give it some indentation, right? Or how about, for example, corrugated cardboard? If it was just like flat cardboard paper, that'd be super flimsy, right? But give it this like truss structure, and now it's a lot stronger, right? So take loads from different sides. You guys remember looking at Tacoma Narrows Bridge? That was actually how they fixed the Tacoma Narrows Bridge. It originally collapsed, they went back, put in a truss structure, all good. So moment of inertia, calculate that. It's like parallel axis theorem in here. Dynamics. If you guys are ever going into mechanical engineering or robotics, pay real close attention in this class. My classmates and I used to call this physics on steroids. Here's an example of a dynamics problem. You guys see sort of an outwitty looking deal here. There's this string tied at angle beta to this cart that might be moving strictly in a horizontal plane. So maybe as this weight falls, accelerates down, maybe a good question would be, how does the motion of this cart change? And that would be dependent on this changing angle beta, right? Ooh, do you see like a bunch of complicating factors, right? So like take you technically could solve this with what you've learned in this class. It would just be like a really, really hard physics problem, like you guys said. So there you go, there's and that. Concrete, right? So there are a couple of materials that are really important to civil engineering, like concrete, steel. So here's what concrete is made of. I forget how much I told you guys first my honors class about concrete, but one constituent part of concrete is water, right? Now, when concrete dries, it's not that the water evaporates, it's that there's actually a chemical process that it actually cures. And that curing process can take years or even decades. The Hoover Dam, I remember hearing about 10, 20 years ago, is like still curing to this day. This process also releases a lot of, I think it's carbon dioxide into the atmosphere. So really, exothermic process actually contributes a lot to global warming. So now, how can you create like different strength concrete or like maximum strength concrete? Or let's look at like this constituent part here, where it says coarse aggregates, right? Think like rocks or like fine aggregates, right? Maybe oh, I almost forgot to mention a very important constituent here, Portland cement, right? So that will bind these aggregates together, right? These coarse fine aggregates. You know what too? This dome I have right here is actually the underside of the Pantheon, which technically is a different kind of concrete because this is ancient Roman concrete. So this is actually not Portland cement concrete, which is the main kind you see all over places like that gray color. This is actually made from like volcanic ash cement. Right? So this sieve, you guys see the sieve right here? Right, the sieve has these different sieve layers that have these different wire meshes of different size holes in them. So if you have some soil sample and you dump it in the top, you see how it's going to separate out the sizes, right? Only the large stuff is in the top, and then everything else goes down. And then only the finest particles, like your like dust and clay particles, can make it all the way to the bottom, right? Through this like very fine mesh. Like I said, okay, so you can separate out, and you can say, okay, well, what type of grade soil do I have? These aggregates, right? And then that can actually predict what strength of concrete you're going to have. Because here's the deal. You guys see this middle one that says poorly graded? Another term for this might be uniformly graded. Uniform is in like, what if you had all the same size rock, right? Well, you guys see how this kind of have lots of voids that would just be filled in by the Portland cement, right? That Portland cement is the weaker part of the structure. The stronger part of the concrete is actually the aggregate, like the rocks. Right? But hey, what if I, instead of just all the same size, like uniformly graded, what if I had like some medium-sized rocks and some small-sized rocks that fill in those gaps, so that there was more proportion rock and aggregate and less proportion Portland cement? That would create a stronger concrete. And so that's well graded, right? So if you have sieve layers where you get like some concrete here and some here and some here, like a pretty good distribution, that might give you well graded concrete, which would be like the strongest concrete. Okay? And then here's gap graded, where you have like just large and small, but like nothing in the middle. Right? Now, one thing I want to mention too is, go back to this uniform grade, right? How big are these rocks? I mean, they might be big rocks, they might be small rocks, but if they're all the same size, do you guys see how proportionally, it would be you could scale this up or scale it down, but proportionally it'd be the same same ratio of like aggregate to cement. So yeah. Oh, and here's a graph, right? So let's look at this graph because you guys got to do graph interpretation for this class too, right? So percent passing by, say in some sieve, and then the grain size increasing to the right. They actually did a log scale here, so interesting, right? So let's start with uniformly graded, like this middle picture. It says poorly graded. That's like uniformly graded, same size. See, that's okay. None small stuff, none, and then bam. Now we get a bunch of medium, and then like no big stuff. Right? Gap grade is like, okay, we get some small stuff, and we're like missing all the medium stuff, and then get a bunch of big stuff. That's like this. Right? And then well grade is like, it's more like continuous. Get some small stuff, some medium stuff, some big stuff, and this is cumulative. So that's why it goes all the way to 100%. All right, different strengths of concrete. Now, if you go to an American university, they actually do use American units. So like PSI, that's pounds per square inch. So you would see that. Now, 2,500 PSI, that's like weaker grade concrete. Here's a mixing ratio of cement to sand to stone. Here's maybe a common use for that. How does that equate to SI units? Well, that's approximately 17 megapascals. Mega is like, so 17 million pascals. Or if you like, that could be 170 atmospheres. We are sitting in 1 atmosphere pressure right now, right? How about the really strong grade concrete at like 4,500 psi, pounds per square inch? Right, here's the ratio mix of materials you'd want. Here's what's be good for. Say if you want to build a skyscraper, I bet those bottom floors better have some really strong concrete, right? And that equates to about 31 million pascals, or like over 300 atmospheres. Right? That stress strain curve. Now, if you go into civil engineering, you will see this graph all over the place. So what is stress, what is strain, and what is this relationship, like the story here? So stress is, okay, force per unit area. Hey, force per unit area, isn't that like pressure, right? Like Newton per square meter, like pascals or pounds per square inch? And it is, but it's just applied to solids. So stress applied to solids. Okay. Now, if you put a stress on a solid, I've got a picture down here showing something in tension. Now, it could be tension or compression. It could go either way. My picture here is showing tension because the force is pulling out, but you could turn it around, same story, right? You guys see some force per this cross-sectional area. So there's your stress. This is Greek letter sigma, right? Lowercase sigma, right? There will be some resulting strain, or strain is a percent change in length. Right? And what is the percent change in length? Well, that depends on the material, right? So if you put the same stress on, say, a copper bar versus a steel bar versus a concrete bar, right? Those are going to strain different percentages, right? Okay, so change in length per original length. There's your strain. That's Greek letter epsilon, right? And there's a ratio between those two, between stress and strain, right? So here's your stress strain curve. So stress going up, strain going to the right. And that ratio for this elastic zone is called Young's modulus. And that is a material property. So there's a Young's modulus for steel, there's a Young's modulus for copper, Young's modulus for different kinds of concrete. Okay? Now, where that elastic zone runs out is the yield point. You guys see this yield point? Now, anything in the elastic zone, you put on the stress, it'll strain a little bit. You take off the stress, it goes back to its original shape. Right? And you can do that a long time until eventually tires out. And so there's a term for that. It's slipping my mind when eventually wears out though. But concrete, actually, this graph would end right there. It got snapped, and it would rupture right at this point. So for that reason, I know that this particular graph probably applies to a metal like steel, because metals like steel have this whole extra bit above here, like this ultimate strain, and this rupture at this strain like way out here on the diagram. Okay? So concrete, bam, like breaks right here, and then like metals can stretch a little bit more. Did I? Yeah, let me go back a slide to here. And so, how do you test the strength of this concrete? And this is one of the classes that you would take. You take concrete classes. Yeah, you guys see these molds here. These molds, I can tell you, are 4 inches in diameter and 8 inches tall cylinders. I know that because I've got an example right here that I nabbed for my own classes back in the day. So you'll take these cylinders, put them in this compressor until it breaks, and then you can get this stress and strain information that you can pop into a diagram like this. Let me switch my screen over and show you guys my show and tell piece. So from one of my classes back in the day, we smashed the cylinders. Let me show you guys. This is in fact 4 inches in diameter. This we are in America, so we're using inches. So there you go, 4 inches. And this used to be 8 inches tall. That would have been, well, this one right here is about 4.5 inches remaining, but so it was like twice as tall originally. Thing got smashed. Grab this, and there. Let's get a close look at this. Let me zoom in here. You guys can see this. Ooh, look at those aggregates. You guys see that? Ooh, different rock sizes. And then that gray stuff in the middle, like the Portland cement, sealing everything together. Ooh, okay. Some associated strength with this was measured in the day. Flip back over. Let's see. Share screen 2. All right. All right. All right. So this is a table for, let's see, different like bars of steel, maybe different manufactured bars of steel. What is the Young's modulus? You see how Young's modulus is pretty much the same number all the way down. This is like a shade over 200 gigapascals because that's a material property. So it shouldn't really vary that much depending on like the size of the bar. But the yield stress, now that is a wildly different number. It goes from like 300 to 700 something, right? Okay, so let me go back, see how is that paired with this graph, right? So the rise over run, that was pretty consistent regardless of the bar shape, right? But the ultimate strength, well, I bet if you have like a really thick bar, right, that this ultimate strength would be a lot bigger, right? That makes sense, right? So same slope regardless because same material, but larger ultimate strength if you have a really thick bar, right? All right, this one here, somebody's got posters hanging from my ceiling here. We're looking at thermal expansion. Oh, hold on. I got to reset this. I just realized it's chopped off my presentation. Sorry, guys. Let me do a quick reset here. Close this presentation out. Okay, right down here. What's that? Okay. Usually this will reset it. Yeah, that looks good. Whoa, nope. Let's watch through the whole thing. Here we go. Right, so one way that say a beam might expand is if it's under like some kind of tension pressure or tension stress. But another way is if you heat it up, right? So now how much would it change its length? That's delta L, change in length, right, compared to L naught as an original length. Right? Based on some temperature change, that's delta T. Delta T is temperature change rate. Well, it depends on the material. So different materials have different coefficient of thermal expansion, and that's what alpha is in this context, right? You guys have seen alpha used in different contexts for different things before. I've used it for angles. You guys see for angular acceleration. I mean, there's only so many letters to go around, including Greek letters, right? But in this context, it's coefficient of thermal expansion. Okay, so here's a table, different coefficients of thermal expansion for different materials. Do you guys see down here at the bottom, steel and concrete have basically the same coefficient of thermal expansion? Now they're showing single numbers here. There's actually a range of values, like a window of values, because there's different types of steel you can make, different grades of concrete. You guys know that. And those windows actually overlap. And that is a very, very good news. And I'll show you guys why. Because you can create steel reinforced concrete. Now, Romans back in the day had their own type of concrete. They used volcanic ash as an ingredient in their cement, which is a little bit different than modern day concrete. Actually, I think it was actually stronger. And they created all kinds of structures with it, right? So they created walls and roads and aqueducts and like domed roofs. Sorry, what's that?
It was like immensely stronger.
Oh yeah.
Yeah.
Okay, yeah. So get verification on that. I don't. Do you have a quantifier or?
Well, mostly just a few cases of Roman architecture still being in like carvings and stuff. And so nowadays, a lot of concrete after like a decade or so tends to dissolve. Like it all crumbles apart, but we still have like structures in the Mediterranean basin that have the ocean come in, but still have this.
All right. That sounds believable. I can believe that. Right. So yeah, what Alex is saying is that like if you create like modern day Portland cement concrete, say like under ocean water, because ocean water is like that'll degrade things, right? It's like so salty, right? So like after a while, like a few decades, like you said a decade or so, or like our modern day concrete will disintegrate. But yeah, that Roman concrete, yeah, I know that I did read that too. They would create these underwater structures that have lasted like over 2,000 years by this point. Yeah. So yeah, that is true. Sounds about right. Now I can tell you what Romans did not do with concrete, though, is they did not create second floors. You guys know we're sitting on a second floor right now. There's a void beneath us. Romans could not build the structure that we're on right now. Why is that? Well, because even though concrete has a huge compressive strength, it has a tiny tensile strength. So just think those toothpick bridges that you guys created. The bottom part goes into tension, and then cracks will form, and this concrete will just crumble really easily. But if you throw a bar of steel down here, like a rebar, then the steel itself can handle the tension part. Now you have a composite material, right? So you guys see that red line represents the rebar, like the steel right here. Okay, so this is a composite material that can handle both the compression and the tension, right? You guys that? You get steel reinforced concrete. And just by a complete quirk of the universe of materials, those materials happen to have basically the same coefficient of thermal expansion. That means that when the temperature heats up and cools down and these materials expand and contract, they expand and contract together, which allows them to not all crack apart. It's fun history behind this. Discovered almost accidentally. There was did I tell you guys about the plant pots when it's originally? Oh yeah, okay. So yeah, there you go. All right, self-healing concrete. So this different modern spins on concrete. So there's this particular extremophile bacteria, and I forget the Latin name, that actually excretes calcium carbonate as a waste product that you can bake into the concrete with like a starch as a food source. Now, concrete will eventually crack and break apart. I know this building feels pretty permanent. Those causeways going across the islands look pretty permanent, but given enough time, they eventually crack apart. So if only you could have a way for this to self-seal, last a lot longer. So what if it cracked apart, the bacteria was exposed, started eating the starch that was also baked in there, excreted the waste product, calcium carbonate, you feel like self-seal that concrete. There's a porous concrete. I don't have a slide for it, but if you look at a city from above, it's like covered in like asphalt. Asphalt's a different type of concrete versus Portland cement, but basically like all paved over, which would disrupt like rainwater flow, right, and like groundwater systems that really disruptive to the ecosystem. But if you have porous concrete, then that's less disruptive, right? Let's look at water treatment. So a lot of things in the modern world easy to take for granted just because you've got to live your day-to-day lives, but flip on the faucet, you get water, clean water, right? Living in a modern country, all EPA check regulated, and then water goes down the drain, flush toilet, and what happens to the wastewater? I'm not thinking much about it because it's easy to forget. It's easy to take for granted because these pipe structures are all buried underneath the ground, so they're out of sight, out of mind, right? But yeah. So water treatment. This whole class I took on this, I've forgotten lots of stuff. I mean, that's true with all these things. But what's some basics? So you have some water source. I think ours is like the St. Johns River, and you want to clean this water, make sure that's like safe for drinking and cooking and using. So in the States, the popular method is to use chlorine to sanitize the water. Over in Europe, the popular method is to use ozone, but different methods, right? It's different process it goes through. And then what about the water that goes down the drain? Well, you don't want to just dump that back into the environment raw because that would cause all sorts of environmental problems. Cities back in the day used to not have water treatment. People just dump sewage seep into the groundwater and get cholera outbreaks all over the place and people dying. So you have to treat this. Now, one detail I do remember, almost forgot to mention, is that these water treatment and wastewater treatment are unique to each locality, right? Like each locality is going to have a different source of water, maybe with different pollutants or different things you might want to treat specifically to it. Same thing with wastewater. There's different ways you can treat it. You can have bacteria there, like eating all the sewage to clean it up. You can burn it. You can capture the methane and burn that for energy, right? Like waste to energy plant. And then last slide here I've got is road construction, right? So most roads are made of asphalt concrete, although there are some that are made of Portland cement concrete too, but asphalt's a little bit nicer, a little bit spongier, a little bit quieter, right? So you'll see the surface of this, but you think about there's this whole structure underneath it. No, we've got like 30 seconds here. Also consider that you might want to put a slight slope on the road so that when it rains, the water doesn't just pool in the middle of the road, right? You want that water to run off. I mean, different design considerations, right? Actually, that worked out pretty good because got about 20 seconds to the bell. But you guys got any questions about either nuclear engineering or civil engineering? All right, you guys ready for lights? Good lights. All right, so tomorrow we'll start on electricity. It'll take about a week to do electricity and circuits, and then we'll go back into review. You guys remember, if you want to review stuff, there's all those resources on AP Classroom. They are there for you guys. All right, you guys have a great rest of your Wednesday.